so much. I would like, first of all, to thank the organizing committee, and especially Ali Genser, for the invitation in this beautiful place, in this beautiful conference. I'm going to talk about the work we've been doing in Napoli on JJson junctions in a long time, and try to answer also to the question that Ali asked yesterday, why students should pick a topic. And I will try to also, with some kind of general overview, extensive overview, to understand why the JJson junction why JJson effect is, the wonders of the JJson effect. It's a pleasure to acknowledge the group working in Napoli. First of all, Davide Massarotti, Domenico Montemurro, who are, young professors in Napoli. Yesterday, Davide gave the talk on about of very detailed aspects. And then I'm going to talk a little bit about the work that Ali Mahmad, Luigi Di Palma, Alessandro Miano did about ferromagnetic junctions and phase detectors. And then also would like to acknowledge Giampiero Pepe, who shares with me a lot of responsibilities for this research. Then also we have a long-standing collaboration with Theory Group in Napoli. This is our Vulcano de Vesuvio, Napoli, and Arturo Tagliacozzo and Saro Fazio. And then also a lot of the things I'm going to discuss later in my talk are due to an intense collaboration with the SIC group. Actually, SIC is a company in the States, but has a research development lab in Napoli led by Marco Arzeo. And so the group is led by Oleg Mukhanov in New York. This is a picture of most of the people in the group. I couldn't do like Jacopo yesterday, the collection it was not so good, but there are different people, there are some overlaps, and there are also some people missing. And also a pleasure to acknowledge some collaboration. There is long-standing collaboration with John Katie and group of Floriano Lombardi and Chalmers, because I'm going to review also some older stuff. And then long-standing collaboration with a group of Mark Blameyer at Cambridge University, and then some recent work with a group of Carmine Granata, Antonio Vettoliera, Siena, still close to Napoli. The starting point is that really we never had so many different types of JJson junctions. That's the starting point of our discussion. And this is due to novel materials, enhanced interface compatibility, novel types of barriers and nanoshapes. So this gives amazing possibilities to investigate exciting physics. Actually, a JJson effect, the nano meets the macro, and we'll see what it means. And then here, we really apply quantum mechanics at the macroscopic collective variable. And then, we'll also discuss how we can really measure the macroscopic quantum. That's really important. So the JJson junction is the tool to measure this phase information, which is in general associated to microscopic entities, is to a circuit. And then, obviously, a JJson junction is a playing ground where coherence and dissipation fight against each other. Obviously, JJson junction can be the answer for a lot of questions. For instance, fundamental questions. For instance, we know about the wave. We will briefly get into that shortly. And then one of the main ideas that also we had some talks during this conference, the idea of putting functional barriers and to have hybrid junctions had been the basis for a lot of proposals to see, for instance, Majorana fermions and topological insulators. And yesterday, I will get at the end also the talk from Nicola Poch and Van der Waal, structures with high TC materials. And then another example is ferromagnetic triplets. And yesterday, Jacopo Santamaria gave a very nice talk on this aspect. Obviously, there are a lot of applications you can think about, and we'll revise some. Obviously, the big one is now the big qubit application in quantum circuits. We'll get into that soon. So these are different kind of structures. These are nanowire based. Here we have topological insulators with flares, graphene. Then the new class of 2 van der Waals materials, and then we have more classical aspects like the ITC and ferromagnet barriers. In any case, JJson junctions are believed to be the keys to answer to a lot of questions. That's our starting point. Then there is something that we should never forget. These are, about wonders. Their special properties. Actually, the collective quantum nature gives us the opportunity to use quantum sensitivity. That's something that we use and we forget how powerful it is, how it's important that we quantize a circuit. It's something amazing that sometimes we forget. And then, obviously, superconductors, all of us know that there's some kind of special properties that they do ideal elements for quantum memories, amplifiers, detector, high-speed processing, and operating over a wide band of microwave frequencies. All these make these ideal candidates for the miracle we are going to see. So basically, the first point is to show that there is some kind of primary quantum macroscopic effect. That is the fact that we're working on the phase of the superconductor. And this obviously is enriched by our capabilities of nanopatterning and of using different materials. But we have to be aware that basically what is used in the qubits is this capability of secondary quantum macroscopic effect that is the real secret of these junctions. So it's for that we can have this kind of magic and pass from a JJson junction to these circuits, the quantum computer, with all these amazing, so here's our basic, but then we enter into readout, control, all superconductors enter different levels of this amazing product of our technology. And we should, like always, to start from this sentence from John Martinis, that actually the superconducting qubit research started in the 80s when we were asking, and particularly refers to Tony Leggett, where macroscopic variables would behave in a quantum mechanical fashion. And this, I'm going to revise quickly these experiments shortly, has been shown by macroscopic quantum tunneling and the existence of quantized energy levels. That we will get to that, and we'll see how these are very special fingerprints to understand the phase dynamics and so to establish if a junction can be used in a quantum computer. We know these are the basic fundamental JJson equation, and here's our primary JJson effect. All you can find in the two Bibles of the book of Antonio Barone and Gianfranco Paterno, in the book from Licareff, Costa Licareff. And here you basically find all possible responses of the phase to the electromagnetic fields and how the circuit approach, how to place this junction. And obviously, in general, we have to take care about these two energies. JJson energy depends on the critical current and charging energy to capacitance. Everything will depend on these two energies. And also, obviously, on how the junction is coupled to the rest of the circuit. This is a typical Fraunhofer pattern that we know has a figure merit of the junction. But this is the first step, and this is what we call the primary quantum effect. In general, we refer to the case where the JJson energy is much larger than the charging energy, and where the phase is well defined. That's what most of the work have been done. Now we have been more and more aware with the qubit advent that it's very interesting also the other regime where phase and charge are not anymore, they play together. And to understand that, and I will get in some detail later, this is the washboard potential that describes the potential of the junction as function of the phase. Through the macroscopic quantum tunneling experiments, we have a proof that these levels exist, that we can have macroscopic quantum tunneling of the whole phase. And so we are entitled to quantize the circuit. That's the basic idea which is behind the qubit. So if we can do that, we can build Hamiltonians, we can build circuits, and we have fun to build complicated circuits and to start the qubit era. And obviously, the two extremes are when we have very well-defined charge and well-defined phase, and this we know are associated to charge qubit, phase qubit, and so far. And we also know that the transmon is the most advanced and also most used, because this solves technically some problems, and this intermediate regime of charge and phase, and is the one more used for all quantum computers. So again, these are the three steps. First, be aware of a collective degree of freedom. Second, experimental observation. So we have to prove macroscopic quantum tunneling and quantization of energy levels, and then we are entitled to believe that we quantize the circuit. These are the steps to follow for whatever kind of technology to be able to be used in a quantum computer. Also, we should not forget, especially if we want to do circuits and to put inside to make it work, that there is something special about JJson, which is the only nonlinear and non-dissipative component. So this property is important for the operation of a lot of superconducting circuits. It's important also for the operation of our transmon and quantum computers. And but it's this is the first part. Then there is also some other part which is connected to more classical superconducting electronics, again connected to JJson junctions, that we can have some transition through magnetic fluxes, and this is the basis of the two logics, apart the voltage pulses, which is the latching logic, the RSQ, which is quite spread in the superconducting community, and there are a lot of applications. And this is from Oleg Mukhanov. I would stress here, without getting into details, that this can work to the hundreds of gigahertz. That's the important information. Then, obviously, there is something magic about the rings, not only mesoscopic physics, but also in superconductivity. And then we have the squids, and we will use that. So we have some kind of loop with two junctions, or one, depending if RF or DC. And just getting to that as utility of having ring in geometry, and so this gives also the opportunity to talk about the pi junction. This is the experiment for the proof of D-wave superconductivity. Here we have also the pleasure to have Dima, was in the original papers in the 87 when it was proposed for ferromagnetic junction. So you have a ring with a junction. If it's a junction, this is the energy profile as a function of flux. If you have a pi junction, like happening for high TC superconducting, this tricrystal geometry. Here we have three junctions, but basically it's important just one to have an odd number of pi junctions, and this is the definition of pi junction. You can have something very special. This is the energy profile, and here you will have a minimum which corresponds to have half-flux quantum. So you will have some kind of spontaneous current that is the proof of the D-wave superconductivity. So here, before it was some kind of powerful result. Now it's so well established that we use that to prove the physics of pi junctions, the wave, and also to understand the power of the ring. But this is inspiring. If you want to test other superconductors, other ideas, you need to do that, because this, again, is some kind of smoking gun experiments. You get or you don't get. If it's the wave, you need to get the half-flux quantum. If you have unconventional permittivity, you need to have that. And here you can also see all other vortices as opposed to half-flux quantum. Here also break symmetry in this case. This is, again, a very inspiring experiment and with a lot of exciting physics. Again, here it's, I would say, another milestone, in my opinion, group of Zhenya Idishov. Here is an RF squid. It's very common today to talk about unconventional critical current phase dependence, and this is the proof that in bicrystal D-wave junctions of the relevance of the second harmonic. So again here, if you have the tool to try these experiments and to prove that if there are other components, the current phase relation, they are important. These are very, It's something very well known from classical superconductors that this is the A is the tunnel-like model, and then if you're in a weak link, there are other harmonics contributing, and in special dimension, you even lose coherence, or the superconducting coherence, for instance, when the micro-BG is too long as opposed to the coherence length. But this case also from very transmissive interfaces, you know that you can have some relevant additional contribution from higher orders, and you will see that in this relation. So it's something that is very established, and again, we have the way to prove that for whatever kind of junction. So there is some kind of clear path to follow if you want to claim things. Okay, so basically, after this general introduction, we'll discuss, we'll take into account these keywords and how the JJson effect can be useful to build smoking gun experiments and more efficient junctions for quantum bits architecture and sensors. Here, obviously, we should, it was already clear from the slides before, but it's always good to keep in mind that basically JJson junction is sensitive to magnetic field, RF field, but depending on the barrier, you can also have some kind of gate dependence on the critical current. This is the concept where there is the gate mode we're going to see shortly, and where there are a lot of applications, the hopes why you put a semiconductor. All the physics now that we are discussing basically use this kind of special material which are sensitive to the gate. Obviously, something that we take care by considering phase dynamics is that we can measure in junctions fluctuations. That's amazing, that by measuring fluctuations, we can reconstruct phase dynamics. So about qubit, we know that superconducting technology is the leading one toward a scalable quantum computer. We know that all computers are based on aluminum technology, except very special case now, a couple of cases. Then we know that JJson junction has a lot of wonders of nature because they can be quantized and can bring quantum mechanics at the macroscopic level. And we know that transmons are key structures. But we also know that we need to improve scalability, error correction. There are a lot of issues to be solved. And from my point of view, I'm happy that there are also some kind of hardware issues, so that the quality of the junctions needs to be improved. So something else has to be improved from a technological point of view, and something else has to be understood also from a fundamental point of view. This, again, is just to be self-consistent, and here I'm not going to comment all different kinds of qubits, but what I want to comment here is that, there's always some kind of counterbalance. You have advantages, you have disadvantages. Some kind of layout allow to solve some problems, some others they don't. And this is the story which now brings to transmon and fluxonium, why sometimes it's better the other one or the other. Here we have some kind of very nice reviews. It's just a very reduced list. And then once you have quantized the circuit, you can build the circuit whatever you want, and this will be some kind of very nice way of building Hamiltonians and build the circuit. We'll see how later we can do that very, very easily. And then this is also the progress of coherence time of qubits that are impressive. In 20 years now, we started from 1 nanosecond to about 1 millisecond. That really can change. So I was talking before about the possibility of gate. I was talking about the possibility that there are things to be improved. That's why, these are, I picked from the lecture without any real order. They are disordered, and doesn't mean that these experiments are better than the other one or two are not. No, but there are some kind of fancy and first reference experiments about the use of nanowires in junctions and this possibility of tuning the critical current by the gate. And this is somehow the follow-up of work in the 90s. There are some examples from the group of Takagi and Haji where he proved some kind of mesoscopic effects in where you have when the barrier is a semiconductor. And this philosophy is behind the proposal, is behind the proposal of the gate mon. The gate mon is a possibility to use other hardware. But basically, it's originated from the fact that not everybody is happy in the transmon design to have the flux line, which gives a lot of noise. So as an example of solution for some kind of hardware problem. These are other examples from the literature, evidence of topological superconductivity, twisted electronics, topological superconductivity. Again, without a special order, they are beautiful works with a lot of amazing technology and a lot of beautiful results. And also, these, again, induced superconductivity in quantum spin Hall edge effect, topological insulator, bipolar current, supercurrenting graphene. And to the point that these junctions have been also suggested as possibility to observe Majorana fermions. And we also heard discussions and proposals here at the conference. Again, here, the point is that fundamental periodicity changing. It's here. So we are talking about a different one from those I showed you before. And again, also in this case, we may have a ring. So we have some kind of example to follow. This has been made for ITC, that we should have some kind of different periodicity on the flux. And these are two examples I've introduced you before. Another way for detecting some very, Majorana physics is, being proposed a fractional JJson effect. Here an example of current phase relationship, similar to the technique shown before by Ilyushev. And again here, I'm just mentioning two experiments, Andrei Zakin is here at the conference, and Akira Furosaki. Just the point that the presence of semi-integer Shapiro steps is not always some kind of sure condition to determine if there are fractional Shapiro steps. And because if you have some kind of non-sinusoidal current phase relation that is typical of highly transparent superconducting barrier, you may have also these additional steps that are not necessarily related to Majorana fermions. And here other examples. And here, for instance, again, from Molenkamp group, obstacles for the observation of fractional JJson effect. There are other effects to take into account if you really want to trust in all fractional steps. So all these beautiful experiments are great. My point of view is that it would be nice to have some kind of electrodynamic characterization, and dissipation would be beneficial to set some more points and to see the really limit of these techniques and these junctions. What do we mean by phase dynamics? Phase dynamics is the capability I just sketched before of understand what the phase does as a function of time. Here's a very simple approach to the circuit of JJson junctions. This is what is called RSJ model, and we can build this equation where we have the capacitance and the normal resistance. So what is beautiful is that we have some kind of mapping of the IV curves on this graph of the potential as a function of the phase. And so by changing the current, we have a picture of what the phase is doing. And by doing these measurements, we have an exact representation of the phase in this potential. And this is the base of the macroscopic quantum experiment that now I want to get into some little details to understand how it works. This is the barrier. This is one valley of the washable potential I showed you before. And we are ramping the current, which is here. Depending on the current, we can change the height of the barrier. And then we know that the first process can happen is thermal activation, and which has this kind of simple dependence of the plasma frequency. Then has been, if we now, this is a stochastic process of the switch from the superconducting to the normal state properties. And this is somehow the picture of what is happening here. So if we plot this switching probability is a function of temperature, like here, we see something, we see some kind of characteristic dependence where, the width becomes thinner and thinner by lowering the temperature and higher the peak. But below some threshold temperature, that in this case, for instance, about 40 millikelvin, we get some kind of saturation of the width. And this means that the process is not anymore thermal, but it's happening quantum. These are some kind of calculation by Caldera-Leggett. What is important to understand is that this depends on the dissipation, the Q factor. If dissipation is high, there is no way you can see macroscopic quantum tunneling. If dissipation is low, and it means high Q values, you can have the process of macroscopic quantum tunneling. Obviously, in order to make sure about that, DC measurements are much harder than RF measurements. And this could be noise. How to be sure it's not noise? Answered by Devoré, Martinez, and Clark were the first one to do this experiment in an extensive way, is that you apply magnetic field, you change critical current by applying magnetic field, you tune plasma frequency, and you tune the crossover temperature. And so, like here, you change crossover temperature by applying magnetic field, and so you are sure that this is not noise, but is an intrinsic quantum effect. So we're talking about macroscopic quantum tunneling. And these are real fingerprints. So these fluctuations are a way of characterizing the phase dynamics and even stating that we have energy levels here and we have macroscopic quantum tunneling. This is a long story, and also, again, for this educational part, the first measurement made by Fulton Dunkelberger, who set up this idea of studying fluctuations. Then there were some measurements also from Bell Labs group and IBM, but with the function of temperature. But then it was set by Martinez, Devoré, and Clark a few years later with a set of experiments. It's not only the saturation. You need to do a lot of fitting. You make to understand how much dissipation there is. And then also they made the first experiments about applying microwaves here and exciting the system from one level to the other one. And again, these graphs are not the first part. Then you need to make sure that there is not noise. There is a consistent way of establishing all parameters, normal resistance, dissipation, quality factor, and so forth and so on. There is another important process here that can happen, and that is phase diffusion. So if the junction has small critical current, and this means that the quality factor is reduced, you may have that the phase is trapped here. And this is important because with all junctions that go towards lower critical current values, like the one I showed you before, this is going to happen more and more, and because the barriers can be more sophisticated, and so it's something that is happening more and more. But what I want to really shortly to make you understand that this, now you can see before it was just decreasing. Now, in this case, it's increasing. What I want to tell you is that, without getting into details, that these are real fingerprints of whatever process escaping and retrapping is happening. And we are very advanced with our current understanding of that by studying these fluctuations for obviously low damping junctions, under damped junctions, to establish the phase dynamics. So here, we have these characteristics. This is the one crossover temperature between thermal and quantum. With the phase diffusion, we have another characteristic temperature where here the sigma, width of the distribution decrease, and here they start to increase. So these are some kind of clear markers of the physics which is happening. And there are also, I highlight here some of the contribution from the Pekola group in Finland and Jim Lukens, who first measured that. And this was also measured before in the Esteve and Devoré for junctions with very small critical current. But it's some kind of same physics with slight differences. And recently, we also did some kind of, by using high TC superconductors. Here, I want just you to appreciate that here is not decreasing some kind of saturation. Here, it just meaning that we are so accurate that we can even tune crossover temperature between quantum and thermal and between phase diffusion and thermal. We can change them. This was made by using some tricks with the capacitance of the high TC superconductors. And so we can somehow build a very nice dissipation map, and we can place the junction in this diagram. And by understanding the JJson energy and the temperature, we can map them and understand the physics. So this just to prove how we are accurate, and even in the high JC regime, like here, for these junctions, we have high critical currents, and what I'm going just again here just to prove the principle is that these apparently may look as those before. You have decrease and then increase. This is the distribution profile, and here you have as a function of temperature. And actually, when you have very high JC, the physics is not anymore ruled by the phase. So this means that in these cases, we did exact fitting and detailed studying. What is going is that some kind of phase leap mechanism occurring, and there are hints of different non-equilibrium dissipation modes. So this may mean that this means that these are different processes. So if you have a switch in this junction may be different. Okay. And so some experiments need to be, you need to understand what kind of switch is the one below. I try to go, I will go faster. And I take advantage of the talk of Jacopo Santamaria yesterday about ferromagnetic junctions, so I don't need to introduce anything about triplet superconductivity and why these junctions are very nice. What this again have been explained yesterday. What I want to point is that we need also here to understand phase dynamics. There are some kind of preliminary or some all works, and actually we have done, this is another reference from a group of Tübingen, and basically what we've done on the junctions of Mark-Blameyer that are ferro-insulator barrier, gadolinium barrier here, with niobium nitride. We have performed macroscopic quantum measurement. We have confirmed that this junction, even if they have some kind of active magnetic barriers, they can be they have a clear phase dynamics, they have macroscopic quantum tunneling, and so they have all prerogatives to be inside the quantum circuit. This also characterization of all these phases of subgap currents, and we are sure that all these junctions are very are ideal from this point of view. About triplet superconductivity, there are a lot of experiments. The main idea is that, as Jacopo explained yesterday, if you observe ICRN for a long depth, this means that only triplet can survive. We have, these are some kind of relevant works on the topic. What we have done also is an alternative way, and this is, again, on this spin filter junction, by measuring properties at very low temperatures. We have seen very anomalous behavior, and this flat area here is some kind of demonstration of triplet. Yesterday, Davide gave an extensive talk on these aspects. But again, here, this particular behavior characteristic of this phase transition. And we also built some kind of map of these temperature dependence playing on the impurity levels inside the barrier. I'm going to the end. I will jump something. Something very nice is also the possibility of hysteretic behavior. So the magnetic pattern shift because of the ferromagnetic behavior here. Here we started with gadolinium barriers, then we have also tried permalloy, palladium ferrum in a different types of junctions, hard ferromagnets, soft ferromagnets. And we also have seen that by applying microwaves, we can have some kind of tuning, so we have for the same magnetic field two different critical currents. And this is somehow the proof, the principle, I'm going fast here, so by applying RF pulses, that we can tune these two-level junctions here with magnetic pulses and with RF pulses. And this is the idea which is behind our proposal of replacing inside the transmon here the traditional junction with a ferromagnetic JJson junction. And this is the paper which recently appeared. And actually here the main advantage is that you don't need to apply a bias line, but it's enough, transmon itself, and you will have you can tune the JJson junction just by applying magnetic pulses or even microwave pulses. And so this works as a qubit sensor. And we have all simulations, and also we have a very important first technological step. To have this kind of hybrid junctions, it's convenient if you want to have complicated setups and some in direction of mixing quantum platforms. And I arrived to this one, and then I'm set. That is an important technological result. We have basically extended the ferromagnetic junction to aluminum technology. Again, we have very beautiful JJson junctions. This is done with Carmine Granata and Antonio Vettoliere. We have perfect junctions, this is figure met, and we also have the typical, in this case, is inverse proximity effect shift of the magnetic pattern. Actually, in this case, we have basically changed the thickness in order to be in this regime. So we have JJson junctions. We take advantage of underdamped behavior with the ferromagnetic junction, which can give the ferromagnetic behaviors. And this is important because it's the first example of aluminum technology with the ferromagnetic barriers, and so it's compatible with all quantum circuits. And on top of that, the idea is that you don't put ferromagnet inside the barrier, but you just put afterwards, and so you solve a lot of technological problems. I go to the conclusions, and I skip all this part about the phase. We figure out the phase detectors, and I just the very last one. That I was very impressed by the talk of yesterday of Nicola Poccia, and this possibility of getting wonderful junctions. This is a great passion of mine. I go back to when we proved the wave experiments in high-TC junctions, and I think that this can be a good candidate for a new generation of quantum device, without putting any limit on it, for quantum device. And conclusions. I think there is a lot of physics in these hybrid JJson junctions. And JJson junctions are real wonder of nature, because not only you can do quantum computing, but you can really play with macroscopic Hamiltonians. And this I didn't get to talk to you, but yesterday David did partly, to invent some kind of new devices, in particular this is a kind of new phase detectors. Thanks so much.
Thank you very much. We also have some time for questions. There is a question over there.
Thank you, Francesco, for this wonderful overview of everything JJson related. I have a problem. Can you comment on JJson effect in strontium ruthenate? Because for quite some time, it considered to be as unambiguous proof of chiral P wave. Then there was this night shift story, and nowadays people say, no, it's not chiral P wave, but ignore data of Liu and companies. So what is
in private. My point is that for some claims, you really need some kind of solid background. You need to do a lot of statistics. You need to wait to say a few things. And so, that's my opinion. Some are clear. The technology behind is amazing. They are amazing. Sometimes some claims can be a little bit behind the step because there is still something to improve. And these I've lived on my own with ITC. In a few years there was an amazing improvement, and at the end we were thinking that there were some effects that were not there, and then you have to wait and to see that. I would say that we say in Italian, tempo è galantuomo, time is a gentleman. And so, but my point is that it's very exciting to see so many different types of JJson junction with so much physics and with so many possibilities. And all these junctions are really a demonstration of the power in the field. Thank you.
Okay, there's another question over there. You already have the microphone.
I'm not expert in this, so maybe this will be completely uneducated comment, okay? But I think that maybe your search for, the search for Majoranas, which you mentioned, is maybe too narrow for this kind of possibility, because if you have a possibility to make a quantum electrical circuit, which you design yourself, then I would somehow look for creating whichever topologically protected state I can make. Why Majorana? I mean, I would really, this is exciting to me in some sense, but the possibility of putting in maybe some, I don't know, maybe some reflections in the waveguides that would create topological twists and so on. I mean, it seems to me you have endless possibilities. Yeah.
I completely agree with you. That was the sense of the talk, just to give this, the feeling of this amazing opportunity. About Majorana, I would like to say that I'm at the head of that. There are some groups which are really doing good research, and for sure, everybody has to be careful about the conditions of the experiments, but is an example. I would say I completely agree with you about the final target, that we have an amazing system, but in the meanwhile, if we can prove other things like Majorana or whatever, they are very welcome.
I'd like to use the opportunity for a last question. 15 years ago, I did some experiments of classical circuits based on normal Josephson junctions and pi junctions based on a D-wave symmetry. And in that case, the junction properties were quite different. And also for other ferromagnetic junctions, the dynamic properties are different. So when you can have this wonder of nature, as you call the Josephson junction, what is the perfect junction you would imagine, or the perfect pair of junction, maybe conventional and pi junction, what you would imagine if everything is free to choose?
I think it depends on the final application. Really, that's the final. Again, I have a long story on ITC, and it's still my first love. and then we are getting so much into ferromagnetic junction. They are really wonderful systems, and they are very flexible. So again, as an example of the application of this idea of the ferrotransmon, that's the name we call this kind of transmon with ferromagnetic junctions. In principle now, we are not thinking of replacing the transmon, to go in the IBM computer. But what I think is nice is to believe that to have more tools, you can have different platforms, and may be convenient to interface with another platform, and that specific junction can be useful. So I would say that you have to see, I would take advantage of the richness of the field and the possibility of having different barriers for different aims. Obviously, if you want to have a superconducting transistor, which is always the ultimate gate, Nobel Prize, the first who will prove it, you want the semiconductor as a barrier. There is no, and so you work on the interface.
Okay, thank you very much, and thank you again for this brilliant review. I like to hand you this, and then we close the session.